that in mind, we move on to the presentation. So in today's presentation, the content will focus on the key drivers that forced us to look for alternatives to the existing and established hexavalent processes. And we aim to provide you with information on the differences between the hexavalent and trivalent electrolytes in terms of bath and equipment requirements. We will also benchmark the deposit characteristics plated from our blue chrome trivalent process against the industrial standard process, which is our HEAF 25. We will present the information related to the process operational differences between the two. So let's move on to the first section of the presentation, which is the key drivers for change. The search for a viable trivalent chrome process is nothing new, and in fact, Atotech has been trying to develop such a system for many number of years. So what's changed now that is forcing us to speed up our development work? The answer is simple, actually. The main driver for the new development is primarily the environment and HSE legislation related to REACH. As you are all aware, the EU has already agreed to ban the use of hexavalent chromium plating in the very near future. And current discussions related to this topic are now focusing on the details of enforcement, which basically means EU is now discussing how to adopt this into a legislation. I will later on in the presentation go into this a bit more deeply. So another factor or key factor which has been a key driver for the new development is the performance of the coating in terms of meeting the current established specifications set by the existing hexavalent chrome plating processes. This in terms of wear resistance, friction, hardness, and corrosion resistance of the coating, etc. So let us now look at the environmental impact of the current hexavalent process. The hexavalent process was first introduced as the Sargent bath formulation back in 1924, and the industry has since come a long way and made a lot of progress on this, and most of this progress was through new processes developed by Atotech. Prior to the 1960s and 70s, it wasn't too uncommon to find operators operating the hexavalent plants suffering from such chronic ailments as holes in the cartilage of the nose cavity caused by years of exposure to chromic acid fumes. Fortunately, we don't see these type of problems anymore because through good HSE practices, we've been able to overcome majority of the problems in terms of health and safety. Nonetheless, the chemistry to this day is still considered as being one of the most toxic in the industry, which is no surprise when we consider that the current chemical formulations consist of chemicals such as chromic acid, sulfuric acid, lead anodes, lead chromate from the anodes, and fluoride-based catalyst systems. So it's no surprise that that the toxic nature of these chemicals attracts attention from the environmentalist groups. The pressure from the environmentalist groups forced the EU to look into chrome plating very seriously from about 10 years ago. And since 2017, the REACH committee, which was appointed by the EU, made proposals to ban the use of a hexavalent hard chrome plating process over the next 7 years. from this sunset date, which was September 2017. And a consortium was set up by the suppliers and users under the name of CTAC, which lobbied strongly to protect the industry in order to avoid an earlier date being set for the ban. And in 2019, the original proposal made by REACH was accepted by the EU Parliament, although no resolution was passed as to how to implement this legislation in detail. Some customers were successful in achieving an extension of a 10 to 12 year due to their specialized application needs. Current status to date is that the EU may consider giving extensions for customers who can prove that there is no viable alternative to their current process for specific applications. However, there is a substantial monetary cost involved in gaining such authorization. We now move on to the next section, which will focus on new developments of a viable trivalent hard chromium plating process supplied by Atotech, that is Glucrum. And we start with looking at the electrolyte first. So the chemistry used for the trivalent process is very different from the hexavalent process. First of all, Glucrum is an environmentally friendly process that complies with all environmental legislations to date. There is no hazardous substances within the composition of the process. In this process, we have trivalent chromium ions, which are kept stable in solution using complexants, stabilizers, buffering agents. The chromium content, of course, is much lower with a trivalent process compared to the Chrome 6 baths. So we're only operating between 15 to 30 gram per liter in Glucrum versus 100 to 150 gram per liter as chromium content in the Chrome 6 baths. The operating parameters such as current density and temperature are very similar to Chrome 6 bath operation. Unlike Chrome 6 baths, however, for a trivalent process like Glucrum, pH is a critical parameter that needs to be controlled. So the operator, when operating such a system, this is the first thing he will probably realize, that there is a main difference between the operation of the two processes. As the Glucrum process is less corrosive compared to the Chrome 6 bath, it is compatible with the cheaper plastic liners like polypropylene. So polypropylene can be used as a tank lining material. No hazardous substances are used within the anode materials. So you can operate Glucrum without lead anodes. Rectifier requirements are comparable. Filtration of the bath is recommended. And pH, of course, pH control is essential for the Glucrum process. The plating speed of Glucrum process at any given cathode current density is comparable to a HEAF processes and is much faster than the conventional bath. And as you can see, it's just a linear relationship between cathode current density and the plating speed. In terms of the bath life of Glucrum electrolyte, this is quite long, and to date we have operated a bath in our automatic pilot line to 900 ampere hours per liter over a 54-month period. So we don't see any issues related to bath age whilst we have been operating this bath. And at two of our customers, we've achieve between 100 and 300 ampere hours per liter. We currently, as mentioned, we currently have 2 customers operating this process under production conditions in their facilities. And as far as efficiency of the process is concerned, as related to bath age, we don't see any variations in this. This is quite stable during the operation of the process. With that, I now hand over to my colleague Alexander to continue with the presentation.
Thank you, Shakil. Welcome everybody also from my side, and now we will go into the next section. Especially we will talk about the layer properties, comparison of layers deposited from blue chromium process versus layers deposited from hexavalent hard chromium bath. So first of all, appearance. Hexavalent chromium layers, they are actually known for their bright and shiny appearance. And actually we can also achieve same with layers deposited from blue chrome. In both cases, we can deposit thicknesses, we can achieve thicknesses from 1 to 300 micrometer. Also, we are able to achieve high quality deposit with adapting some polishing facilities so that we have comparable result for hexavalent and blue chrome layers at the end. The big difference is that the layer deposited from blue chromium bath have more macro cracks. So if you can have a look on the left side of the presentation, you can see here we compare cross sections of chromium layers for hexavalent chromium process HEAF 25 and blue chrome. So you see, if you have a look on unedged cross section, in case of HEAF 25, you will not see any cracks going through. If you can see the edge part, there some tiny micro cracks are presented, which provide also good corrosion resistance. In case of layers deposited from blue chromium, you can see also, even with naked eye on the surface, not naked eye under the microscope, you can see some macro cracks. You can see some cracks, and in cross section you can see unedged, very tiny, and if edged, you can see that there are some macro cracks going through the whole layer to the substrate. What does it mean? This means that there is a big influence of the microstructure on corrosion, first of all. So if you can see on the right side, a cross section again of chromium layer deposited from blue chromium bath. You can see the micro cracks, but you can see also macro cracks, which going through till the substrate. This means that having these macro cracks will prevent corrosion protection, as in this case, you have the corrosive, for corrosive media, you have direct pathway to your substrate, steel. That means that very soon you will see the corrosion spot on your chromium, like red rust. Therefore, to avoid this, we need a dense intermediate layer in between steel, the substrate, and the chromium. And this layer will provide necessary corrosion resistance. So layer of choice might be semi-bright nickel. Semi-bright nickel has high corrosion resistant itself, at least in case of neutral salt spray testing, which is also commonly used for our application. And using this nickel underlayer, you can easily achieve several hundred hours without base material corrosion. So here on this slide, you can see the comparison of corrosion rating neutral salt spray test after 240 hours of testing. And the comparison is done for parts deposited from Hexavalent, our benchmark HEAF 25, and blue chromium. In both cases, we have comparable chromium thicknesses on top. For blue chromium, we have also semi-bright nickel underlayer for the parts. And the parts deposited from HEAF 25 process, they were taken like from production, and they have seen the post finishing like heat treatment, and they were also ground. So in case of parts deposited from blue chromium, you can see that we present here comparisons of different post-treatment conditions. Like the first one, there was no post-treatment done, so parts as plated. And for these parts, you can see the same corrosion rating as for parts from HEAF 25 process. But if we are looking closer for parts which have seen some post-treatment, like heat treatment or polishing, then we can see that corrosion resistant increases for these parts. So very short explanation why we compare here two different temperatures, like 110 degrees C and 220 degrees C. You will see this temperature also later on another slide. This is because it dependently of what our end customer is doing and what will be done with the parts. Sometimes the end parts will be like subject of hydrogen embrittlement process, which is done at certain temperatures, or maybe just parts will be in use and they will be heat up to a certain temperature. That's why we compare these two. Also worth to mention, chloride resistance. So blue chrome, if we compare with parts deposited from Hexavalent HEAF 25 process, they have superior chloride resistance. So if you can see here on the left side, there is a part deposited from Hexavalent chromium after 96 hours of testing with calcium chloride solution and kaolin. You can also meet sometimes like Russian mud. And you can see that here, after 96 hours of testing, in case of hexavalent chromium layer, especially layer deposited from hexavalent chromium electrolyte, already some corrosion products can be seen, chromium corrosion. And on the other hand, on the right side, blue chromium, you don't see any signs of corrosion presenting after the same time of testing. So why this happens? Actually, also because the chromium layer, which we deposit from blue chrome, is not pure chromium, but containing also some small quantity of carbon inside. And that's why this is our explanation why the corrosion resistance is better for chlorides. So here on this slide, what you can see, this is a very nice example from our customer, from field experience with hydraulic rods. And in this test, our customer, thank you at this point for Ovacoret and also for providing these pictures. So our customer simulate behavior in hard marine environment. So severe environment where the concentration of chlorides and also other ions is high in sea water. And for this test, the customer manual spraying this corrosion solution, this sea brine, on vertical bars Then drying is at room temperature, and this procedure is repeated every day, and the parts are examined every day, and at the end, the goal is to determine time till corrosion of chromium starts. And you can see here 2 bars, and one is where you don't see any degradation of the chromium layer itself. So this is the part deposited from blue chromium. And also you can see the part which was deposited from hexavalent bath has some oxide, chromium oxide spot, which appear already after 6 days of test. So next important point, what is about the hardness? Chromium is very loved for this property like hardness. And here you can see again the comparison of parts of layers deposited from blue chrome and Heave 25. And at this point, I have to admit that if you compare hardness, that you need to be sure that you compare hardness measurement done by the same method. So in this case, the hardness was done on cross section. For that, the layer thickness must be big enough. And here you can see that the layers deposited from blue chromium, in fact, they are a bit softer if you compare with Heave 25. However, if you apply post-treatment, like heat treatment and grinding polishing, then doing that, you introduce certain heat into the layer. And because there is some carbon inside of blue chromium layer, from certain temperature and after certain time, the chromium carbide phase will be built, and it leads to the layer hardening. So here on this slide, you can see very well how the hardness is evolved with time and temperature. So like at temperature like 80 degrees C over the time, not much hardness increase to be expected. But if you go for higher temperatures, in this case 200 degrees C, then you can see that both temperature and also time are important. And to summarize the hardness, we can say that in fact blue chromium process, the parts have similar hardness to conventional hexavalent chromium, but at the same time, they are a bit softer as Heave hard chromium presses if as plated. Okay, very important also to compare the roughness. So roughness needs to be okay at the end. And as you can see, the parts deposited from blue chromium just as plated without any treatment, they have a bit higher at that value. This is, in fact, depends, of course, from the substrate. What is the quality? What is the roughness of substrate? But also due to a bit different growth mechanisms of layers from blue chromium, a bit higher roughness can be as plated. However, what is important here to see that if applying post-treatment like post-grinding, post-polishing, it is possible to achieve even better result as for parts deposited from Heave 25. However, at this point, it must be said that doing that, some adjustment of parameters, of grinding parameters need to be done. As the chromium layer, blue chromium layer is softer if compared to hexavalent, you need to apply also more softer grinding conditions to achieve at the end the same or even better quality. Coming to the wear. So here you can see the results from well-known Tabor test, where rubber wheel is like cyclically moving against chromium surface and the mass loss is determined at the end. So here you can see that in fact abrasion resistance for layers deposited from blue chromium is like between conventional and heave process. So we can say this is comparable. However, if we go for parts which have seen some heat treatment, this is the results from the same Tabor test, but for parts without and heat treated for blue chromium. So you can see that when you increase the temperature, the post-treatment temperature, the mass loss might increase a bit. So that is because the brittleness of the deposit also changes a bit due to hardening and crack widening of blue chrome during heat treatment. Coming to the next point is friction. So coefficient of friction. At this point, I have to admit that there are several methods of determination of coefficient of frictions. And that's why also if you compare the data, you need also to be sure that you compare the data which were produced by the same measurement machine and method, especially method. So here what we have, the method is pin on disk. And what is happening, the sliding wear of the deposit is determined against a moving ball. And this moving ball, this so-called antibody. And this antibody can be made from different materials. And in this case, for this test result, it was hardened steel. So this test is applied for determination of resistance to sliding, wear, and friction for non-lubricated or lubricated contents. And in this case, it was non-lubricated. So for this method against hardened steel antibody, we obtained comparable coefficients of frictions for blue chromium and heave surfaces. So we didn't see any differences. Now coming to the next point, like process operation. Here on this slide, you can see left side is the process sequence for usual hexavalent for plating of chromium from hexavalent bath. And on the right side, the same for blue chromium. You can see that, in fact, the part like mechanical pre-treatment or post-treatment will remain the same for both, but the part where, in case for hexavalent chromium, first the parts will be cleaned, then the subject of anodic etch can be, and then later the parts go in for chromium plating. For blue chromium process, this part is a bit longer. There are a bit more plating steps involved, like degreasing, pickling, electrocleaning, activation, then maybe nickel strike prior to semi-bright nickel, and so on. So in fact, you see that there are a bit more plating steps are involved, but at the same time, all the steps are standard for every galvanic nickel plating on steel. Like this is a standard general metal finishing process. And yes, there are a bit more steps involved. As I said already, you can go for nickel strike prior to semi-bright. This is because, yes, the base material mostly this is steel, but not every steel is the same, and depending on steel, if it's higher alloyed steel, maybe you will need nickel strike in between to achieve good adhesion. So also important point is to mention some words about anodic etching. So it is common for hardened steel parts to be ground or polished after shaping or milling. These treatments can, by the way, cause or leave surface defects that can affect the quality of the final part, and especially subsequent finishes like plated layers. So the common issue, what can be seen during grinding, like sliver formation from tubes which not been completely removed from the surface. And during the subsequent steps like activation, these slivers can stand up, then they will be covered with chromium. After that, the parts will be post-finished, and in that moment it can be possible, well, a certain layer is removed of a certain layer of chromium from the top is removed during grinding, that these slivers will become open, and then you can have the direct corrosion pathway, and red rust will appear very soon. So this is to overcome end-usual hexavalent chromium by using etching in chromic acid, like etching in hexavalent chromium bath. It can be separate tank or the same. This is a common issue, like reverse etching. You cannot do this in blue chromium process, so this will not work. But to overcome these issues, we have the solution, and this is like electrochemical pre-etch for the parts which might have these problems. And in this case, this is, yes, electrochemical process. After that, you might need to apply anodic electrocleaning, like so-called dismatting, then activation, and then you go subsequently for nickel and blue chromium plating, and at the end we are able to achieve same results like if in fact in case for etching in chromic acid. So smooth, nice deposit are achieved at the end. So let's go for some process comparison. Like if we are going to our customer, that we provide, of course, technical data sheets for both hexavalent or Trivalent Hard chromium blue chrome process, when then the chemistry is like observed using SPC chart, the chromium content is determined on site, and some additional analysis done by our local Atotech centers. If we compare material, as Shakil already mentioned, for blue chromium, you don't need to go for expensive PVDF material for tank. You can just use PP, it works fine. Then again, you can use inert graphite or MMO anodes. For blue chromium, for hexavalent, we know that you need to use lead. For blue chromium process, however, this is required to use titanium clad copper for bars, cathodic anodic bars. That is not the case for hexavalent, where you can also use copper. For both processes, you will need to use exhaust due to misting, due to hydrogen evolution, which takes some parts of electrolyte, and you will have misting. For blue chromium, you will need some basic electrolyte agitation and some filtration is required. Also, for equipment, important, a part of another stuff which Shakil already mentioned, it is important to have pH meter because pH is important for blue chromium. And also, you may need some auxiliary equipment. In fact, for both hexavalent and trivalent, but for trivalent, for example, you might need maybe ion exchanger to remove some contaminations. So, coming to the summary, I thank you for your attention and I will hand over back to Shakil. Thank you very much.
Thank you, Alexander. So going on to the summary, one thing I can say proudly that in keeping with Atotech's traditions of being the first with new process developments for functional chrome plating, I mean, Atotech and its former subsidiaries were the first to develop the heave system, and also the self-regulating baths. So in keeping with those traditions, we can say that blue chrome is the first commercial trivalent hard chromium process in the marketplace. So this is a clear statement to say, yes, we have a process which is now commercially ready for your use. It fulfills all current and forthcoming environmental legislations. It meets all quality requirements offered by the hexavalent-based processes in terms of wear and corrosion resistance, as well as other properties. The process is stable and has been used under industrial conditions. However, it does include more steps compared to the traditional Chrome 6 processes that we are familiar with. Atotech has in its technical center in Bangalore, India, a fully automatic plating line dedicated for blue chrome, which is available for your sample plating. We also have pilot lines dedicated to blue chrome in our facilities in Berlin, Italy, China, Japan, and the USA. And again, this is for customer sample plating. That concludes our presentation. And on that note, I would like to say a big thank you to all participants for patiently listening to our presentation. And I now hand over to Anya for the question and answer session. Thank you.
Thank you, Shakil. Thank you, Alexandra. We will now proceed with the Q&A session. I would like to remind you that we will cover as many questions as possible during our session, and all the rest will be answered by the WRC team after the webinar via email. Okay, let's start. Question number 1. Some trivalent chromium formulations contain boric acid, which is hazardous for health. Is this the case also for blue chrome?
I guess I will answer this question. So usually we would not answer the question regarding the formulation, but this is an exception because, yes, in fact, you can meet a lot of literature. You can find a lot of literature formulations for trivalent electrolytes containing boric acid. That is true, but that is not the case for blue chromium. So blue chromium electrolyte is completely free of boric acid. Thank you.
Thank you. The next question about the process. You mentioned pH is critical to control. How is this measured?
In the presentation already, Alexander mentioned the use of pH meter. So we can measure the pH in the bath using pH meter with special pH probes. All of this information we can share with individual customers when they are interested to install the Glucrum process. We will advise as to what type of pH meter and what type of pH probe that is required.
On slide 16, where there were calcium chloride samples plated, those samples plated with nickel strike layers?
Slide 16, I guess this is for calcium chloride. No, these parts, they were plated not with nickel strike. So this is like a semi-bright, like steel, semi-bright nickel and Glucrum on top.
Okay, coming to the next questions. Nickel underlayer is required to provide sufficient corrosion protection. Any requirements for nickel?
First of all, we need to understand that the function of the nickel underlayer is to provide adhesion and also corrosion protection. And the function of the Glucrum is to provide the wear resistance on top. So as far as the nickel underlayer is concerned, Atotech has developed a specific electrolytic nickel plating process called Glucrum nickel, which we recommend for use with this. And the objective of this process is to provide semi-bright deposits which have good adhesion and good ductility, as well as good corrosion protection. In some cases, some of our customers have also done some tests with electroless nickel coatings, and these can also be applied. But we normally recommend that you use Glucrum nickel as the underlayer.
Okay, thank you. The next question, what is the lifetime of the process?
I presented a slide showing some information on this at the beginning of the presentation. Currently in our tech center, we have a bath which has been running for the past 2 years, and we've achieved 900 ampere hours per liter out of this bath. And so far, we don't see any negative consequences of aging. So for us, there is nothing to make us believe that there is any problems related to bath age. So in our opinion, you can use these baths for a very, very long time.
Another question, what are the various types of contaminants that can affect the Glucrum process?
So maybe I can answer this question. So what are the contaminants? Like, first of all, we should talk about metallic contamination. Like, for example, if during operation one part, the substrate part, will for any reason fall down into the electrolyte, then this will corrode, and then the iron concentration in bath will increase. And this might lead to, from certain concentration, this you will see like black areas on the deposited parts. The same story is if you, for example, use the anodic and cathodic bars, which are not titanium cladded, but just copper. Then this copper will corrode with time, and the copper concentration in electrolyte will increase again from certain concentration, this will lead in black areas on your plated part, especially in low current density region. Also, this might be the case like for nickel. Can be that you that the nickel contamination come from the previous steps, plating steps, and so that is what we can say might be critical: iron, copper, and nickel metallic contamination. And for that, to avoid or to remove these contaminants from the electrolyte, we have a solution in terms of ion exchange unit.
All right, thank you, Alexandra. Next question. In terms of operating temperature, what is the highest temperature the process can be operated at? And are there any consequences for exceeding the recommended temperature?
I can answer this question. We normally specify that the best temperature the process is operated under is between 45 and 55 degrees centigrade. Increasing the temperature higher may have some negative consequences towards the deposit appearance, for example. Alexander, maybe you can offer some suggestions in terms of other negative effects which could be due to the higher temperature.
Not really, Shakil, not really. So it might be if you have to keep in mind, if you go for higher temperatures, also the evaporation rate of your liquid. This is liquid. This will be higher, so that you might need to make to fill it with water more often. But in fact, I guess you answered the question.
Okay, thank you. Next question. What is the composition of the chromium deposit, and does it contain any other metals?
Maybe I answer this question. So as I mentioned already, the coating, the layer deposited from blue chromium, it's not pure chromium itself, but it contains like about 1 to 5% by weight of carbon inclusion. But at the same time, we do not have any another metallic alloying elements inside. So.
Another question on deposit properties. Is hardness uniform across the deposited layer, or is it affected by different cathode current densities?
In fact, the hardness is uniform across the deposit layer, yes. And that is not affected by different cathodic current densities, but more by the temperature, as I shown at some slide. So if you go for higher temperatures, you will rather see the changes in hardness as if you play with current densities.
What kind of internal stress has blue chrome?
So maybe also I can answer this question. The blue chrome has the layers deposited from blue chromium. They have tensile type of internal stress. And at this point, maybe it makes sense to add that for this reason, we also recommend that the nickel, the underlayer nickel, has also tensile type of stress, because otherwise, if you combine the quantities with two different types of stress, you might have some issues like blistering and so on.
Thank you. There's another question. What is the minimum thickness required to achieve sufficient corrosion protection?
So maybe I can answer this question. To be honest, the thickness you require will be dependent very much on the type of application you are looking at. And for sure, we can advise for specific applications what the best thicknesses are for both the nickel layer and the blue chrome layer. But normally, for example, if your application, as a standard, we say that you plate 10 microns of nickel and 20 microns of blue chrome to achieve 240 hours in neutral salt spray. But if your application, the corrosion resistance is not the major requirement and wear resistance is much more critical, then you could probably reduce the nickel thickness down to maybe say 5 microns and put a slightly thicker blue chrome layer on to handle the wear resistance. Alternatively, if it was the other way around, where corrosion resistance for your application is the main priority, then of course we would recommend that you plate maybe 10 to 15 microns of nickel, followed by 5 to 10 microns of blue chrome, for example. So this really depends on the type of application and the type of environment that the finished parts will be subjected to.
Next question, can this new can this new technology be used in the industrial level? Like, for instance, 40 centimeter diameter and 1.4 meters length bars?
So going by the work we have done so far, we don't see any reason why you cannot industrialize it for such large parts. In fact, the customers we currently have operating are using the process for plating hydraulic bars. So there's no issues in terms of the size of bar that you are plating with blue chrome.
Another question, does blue chrome also have uneven chrome layer thickness, especially on the ends?
Maybe I can answer this question. So in fact, I think the question is more like about the dog bone effect, so-called. So in fact, the performance of blue chromium is comparable to hexavalent chromium. So yes, if you will have very lone parts, then in areas of high current density, it might be necessary that you need to apply some shieldings to achieve the homogeneous thickness distribution over the whole long part. But yes, this is definitely possible.
Okay, one last question. How is the stripping of blue chrome done?
How is the stripping of blue chrome done? There are several options for that, I would say. So it is, there might be electrolytical stripping, or you can use also just chemical stripping. Yeah, so there are several options.
Okay, thank you. Thank you, Alexandra. Thank you, Shakil. Thank you, everyone.